Hey everyone, quick video on titrations. This is the last topic in our solutions unit, and I will go on record and say it's one of the most important things you will do in Chem 11. I like almost ending with this. It's an accumulation of quite a few things that we've been practicing throughout the year. A lot more to say about it in class. 2-3 days worth of labs coming up, which should be a lot of fun. And this typically is your lab final. So let's start talking about what's going on here. A titration is a really specific type of lab procedure and a really specific calculation. You have actually done this calculation already in this course. I just chose not to use the word titration for it. The apparatus you see on the left of the screen is simply a long tube of burette, which some of you have some experience with already. It's got a volumetric flask down below. In the burette, you have a standard solution. This is a solution that you will make, so you know the molarity of it. It has a specific number, usually a nice whole number, 0.300, 0.150. A nice easy number to calculate, measure, and use. The sample is your unknown. It is the solution that you do not know the molarity for, and you need to end your calculation solving for molarity. What you do know for your sample solution is the milliliters. We will always be using a 10 mil sample, 20, 25 mil sample. It's usually a nice, easy, whole number that you get to pick. You just got to record what you use. So we will add drops of our standard to the sample. And when there's a color change, which that is beyond the scope of Chem 11, we'll learn about that in Chem 12, the titration is over. When the titration over, we say you have reached the equivalence point. Again, the full detail of this is beyond the scope of Chem 11, but you will learn this lab perfectly this year, and then we'll dive into the details next year. So, what exactly did I just say? Well, I just described you using 3 different numbers. Okay? So this is your typical titration question. I think it's actually easier in real life as a lab, which is why we're going to be doing one tomorrow. In a question, I highly recommend you draw out what you have. You have your burette and you have your sample. We have our standard and we have our unknown or our sample. And I think you should write in here what you know. So it says, solution of HCl of unknown concentration was titrated with 0.15 molar barium hydroxide. The equivalence point is reached when 14.83 mils of blah 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 is added to 50 mils of HCl. Your standard is 0.150 molar, and you used 14.83 milliliters of it, and your sample is 50 milliliters. Your standard is barium hydroxide. That's what you are using. And your sample, what you're trying to find, your unknown, is HCl. There's no specific order in which you should write these out. You want to write it out in any order that your brain catches it while you read the question. Obviously, what you're trying to find is going to be labeled a sample. You just need to know it goes on the bottom. What you're using is always going to be on the top. It's always going to be in your burette as your standard. Now we just have to use stoichiometry, which we have studied to death back in Unit 3. Go through a balanced equation, use the mole ratios, and end the question with molarity. Believe it or not, you have already done this. We know there are 4 or 5 ways to get moles: grams, liters at STP, molecules, and molarity. So if you have molarity, the formula is moles over liters. We want moles, so you are going to start with liters times molarity. And it's not a coincidence that you have a liters number and a molarity. You multiply those together, you get moles. You want to convert that moles into moles of something else with the ratio, the 2 and the 1. You will end up with moles of something new. And this is actually moles of your sample, because that's what we're trying to solve. You have your moles of your sample, you can divide it by your liters of your sample, and you will end up with molarity of a new compound, in this case HCl. So this is just stoichiometry with molarity. We're not using grams, we're not using molecules, we're not using liters at STP, we're not using individual atoms. You're just using the molarity formula in a couple of different ways. So here's what it looks like. 14.83 milliliters into liters is 0.01483 liters times the molarity, 0.150 molar. The ratio, what you want, is always on top. 2 moles HCl over 1 mole BaOH2. Classic question is, how do you know that goes on the bottom? It goes on the bottom because you started with that thing and you got to cancel it off diagonally. I did not leave myself a whole lot of space here, but you'll see what I mean in a minute. This gives us moles of HCl. I like to write out that number. Moles of HCl, and we want molarity, which is moles over liters, and the liters is 50 milliliters. Move the decimal. 0 liters, and that will give us our final answer. 0.01483 times 2 divided by 0.05 gives us a final answer of 0.08898 molar. Now, do you need that number there? I don't know. I'm not going to bother writing it down. It's in my calculator. Liters times molarity times the ratio divided by liters. You start with your standard, and you end with your sample. Every single titration question on the planet looks like this. Can have grams at the end. The titration is really the lab procedure, but this math is just stoichiometry from a couple units ago. I will always suggest you draw this thing out here in blue. I'm going to ask you to do that on our quiz and test. I'm going to ask you to label the standards in the samples and the milliliters and the molarities and the formulas, and I've had great success over the years with that. So let's try it again, shall we? This question looks totally different, but it's more realistic to real life data. In real life, when you perform your titration, you will mess it up way more times than you get it right. So in your lab tomorrow, you're going to end up doing 7, 8, 9, 10 titrations, and you're going to pick the best ones. The best ones are when you get 3 values that are repeatable. Now, I'm not going to give you 10 different trial data here because that'll take too long. So you'll understand where these numbers come from in your lab. But your burette, big long tube, has 0.00 up top and 50 on the bottom. So you fill your burette up to about the 0 mark, and in this titration it's over when it reaches 9.02, which means you've added 9.02 milliliters of your standard. You're starting your next trial at 9:02, which isn't exactly correct, but I'll explain that in the lab tomorrow. And it went to 17.95, which means in your second trial you added 8.93 milliliters of your standard. Those seem pretty close. Your third trial started at 17.95 and it ended at 26.89, so that means you added 8.94 milliliters. Maybe you do a trial 4, maybe you do a trial 5, a trial 6, and so on. For the purpose of this video, we are going to say we're going to ignore trial 1 because the value is too far away. From my understanding, in university, your goal is to get this to plus or minus 0.1 milliliters. And believe it or not, it might even be 0.01, but I'm drawing a blank for some reason and I can't pause or edit this video, so I'm just going to admit that. We're going to shoot for 0.1 tomorrow. You should be able to get it within about a drop, and that's pretty spectacular. So we're going to cancel off trial 1, and usually trial 1 is a mess because you don't really know the end, and you get better and better and better as you go through your lab, and you'll see all this. As a teacher, I have a lot of fun watching you fire through a titration lab. You'll really enjoy it, and you'll feel like a huge geek, but that's the whole point. So here we go. Let's do the math. 0.2 molar NaOH, 3 separate 50 ml samples with an unknown H2SO4. So let's draw that out, shall we? We are going to have our burette. This is our standard. It was NaOH. It was 0.200 molar, I think it said. And our sample is down here. It was H2SO4. And it was 50 mils. The only number I'm missing is the average milliliters required to reach the equivalence point. In the first question, you were just given that number. In this question, you're going to average trial 2 and 3. And when you average these, you're going to get 8.935 milliliters. So that's up here, 8.935 milliliters. So every titration question will be liters times molarity times the ratio to give you moles of your sample. Then you divide that by liters of your sample, and you'll end up with molarity. So here it is, 0.00895 liters times 0.200 molar times the ratio. We'll scroll up to the balanced equation. What we want is 1 mole H2SO4. We are using 2 moles NaOH. We will end up with some number moles in my calculator, and I'm dividing it by the 50 milliliter sample in liters. 5000 liters. So 8935 times 0.2 divided by 2 divided by 0.05. 0 point, what do we need? 3 sig figs. 0.179 molar. Boom. That's all there is to it. It's way more fun in the lab. Trust me, when you're counting drops, looking for color changes, arguing about if it needs one more or not, it's going to be a great time tomorrow. These two examples are the classic lab type scenarios. There are other versions of this which you have done already in a different unit with stoichiometry, where you can end with grams or end in liters. if you're given molarity of your sample, but then it's not a real titration, it's just a paper pencil question. So here is just one more titration question. 19.8 mils of whatever, unknown concentration, reacts with that and that. There's your formula. We did this question back in Unit 3, where you are going to start with liters in molarity to get moles. You go through your ratio, and then you divide by that. It's unbelievably repetitive. Some teachers will say you don't need to convert it into liters. I fully agree with that. You can do this in milliliters if you want. We'll talk more about that in class. So let's just keep going into liters. So liters in molarity times the ratio will give us moles, and you want to divide that by liters, and you'll end up with concentration. And that's what we want to find, concentration. So 0.0250 liters times 0.500 molar times the ratio. We want to end with H3PO4. That's got to go on top. We've got to cancel off KOH. So 1 mole H3PO4 over 2 moles KOH gives us some number divided by 19.8 milliliters. Sorry, that needs to be in liters. I'm used to doing it in milliliters. 0.198 liters. Then we'll be done. 0.025 times 0.5 divided by 2 divided by 0.0198 equals 316. And that is rounded to 3 sig figs, which is what we need. Okay, one more. Minor variation, and I know I sound like a broken record, but this is just stoichiometry with a molarity formula, not grams, not liters at STP, not molecules. You start with whatever information can give you moles. We need to end in volume, we have molarity, and we have liters times molarity to get us moles. So 0.125 liters times 0.250 molar times the ratio. This is H3PO4 and KOH. Let's just use the balanced equation from above. We want to end in KOH. We want that on top. 2 moles KOH over 1 mole H3PO4. This will give us moles of KOH. We want liters, and big M is moles over liters. So liters is moles over molarity, and it's not a coincidence that you are given a molarity. So put that in, you'll end up with liters. 0.125 times 0.250 times 2 divided by 0.2. 313. 313 liters. Chances are you'll measure that out in milliliters. So it'd be 31.3 or 300, whatever. You know what I mean. 0.13313 liters. There it is, crew. See you tomorrow.